Hi, welcome to IEEE Sensor Conference. My name is Mohammad Rejwanul Haque. I am a PhD student at University of Alabama. Dr. Masudul Imtiaz is our postdoc in our lab. Dr. Xiangrong Shen is a professor in mechanical engineering, and Dr. Sazonov is a professor in electrical and computer science engineering at the same university. In this presentation, I'm going to talk about real-time level ground walking versus stair-climbing locomotion mode detection. There are about 2 million people living with limb loss in United States who are suffering from mobility issues. Power lower limb prosthesis is a promising technology that can provide a greater ability and mobility to transfemoral amputees. One major concern of research on robotic lower limb prosthesis is the locomotion mode recognition, which is very important for the effectiveness of the high-level controller to allow amputees to perform automatic, seamless transition between locomotion modes. However, current methods to detect modes, such as visual or movement commands, are unintuitive and impose a cognitive burden. An ideal system would provide a safe, automatic, and seamless detection locomotion modes without any cognitive burden imposed on the user. The goal of this study was to develop a wearable locomotion mode recognition system capable of recognizing level ground versus walking and stair climbing in real time. A wearable exoskeleton system is used to mount the sensors for accurate lower limb motion data collection, which consists of 3 segments, including a thigh segment, a shank segment, and a foot segment. These segments are connected by 2 joints. The shape of the thigh and shank segment can be adjusted to align the user's cuff curvature using orthotic bending irons. Also, the height of the exoskeleton is adjustable with a range of approximately 7.6 centimeters, which enables the device to fit subject at different heights in a configuration that ensures the joint sensor is fixed on axis with the rotation the measured joint. 2 IMUs of the data acquisition system were placed on the shank segment. On the thigh segment, to effectively perceive the movement information. The force sensing resistors are embedded under the shoe sole, were installed at the main force point to measure heel and ball pressure under the foot. The sensor system used in data collection consists of 2 IMUs, 2 FSRs, and data acquisition electronics with a 3.5 volt lithium polymer battery of 300 milliampere hour capacity. This system employed STM32, a Cortex M4 ultra low power ARM microcontroller, a 16 GB micro SD card to store data sample at 1 kHz. The sensor suite was capable of monitoring accelerations in all 3 directions, rotation around its axis, and change in resistance upon applying pressure or mechanical stress. The IMUs were interfaced with the microcontroller through 2 SPI interfaces. The polymer thick FSR is capable of measuring pressure utilizing its property of decreasing resistance with the increase in the applied force on its active surface. A resistive divider was formed by each FSR and a 500 ohm resistor and applied to a op-amp based voltage follower. The op-amp output of the FSR was interfaced with the microcontroller through 2 ADC channels. To collect data for this study, volunteers were recruited. 2 volunteers with no physical and cognitive abnormalities participated in this data collection. The study was approved by the Institutional Review Board at the University of Alabama. First, each subject was asked to wear the sensor system. Before starting the data collection, the subjects were asked to walk normally for about 5 to 10 minutes to get comfortable with the device. After that, they performed following locomotive activities in the following order. First, level ground walking in self-selected moderate and fast cadence. then a stair ascending starting at ground floor to the third floor. All participants repeat the same activity sequence for 20 times. The participants were free to take rest whenever necessary. A total 85 minutes of data, approximately 51 minutes of ground walking, and 34 minutes of stair climbing was recorded by the system from the subject. The data contains the value of accelerometer and gyroscope for X, Y, and Z axes from both IMUs, as well as the heel and ball pressure from FSRs. The figure shows an instance of thigh IMU sensor responses while a participant was walking, then stopped for a moment and started stair ascending at self-selected speed. The dataset was manually reviewed and then labeled by a custom MATLAB application for model training and validation. Initially, 112 features, 8 features from each signal, were defined and extracted from all sensor signal. Simple and computationally less intensive time domain features were explored for easy real-time microcontroller implementation. The features we selected are shown in the screen. To find out the most significant features, a forward feature selection technique was implemented. This was an iterative method which started with having no features in the model. In each iteration, a new feature was added which best improved the modality, and addition of a new variable did not improve the performance of the model. A total of 10 features were initially determined from the forward feature selection method, which are listed in the right side of the screen. Since too many features may lead to overfitting, to find out the best performing set of the features, the accuracy of the model for different combinations of features were investigated. The linear discriminant analysis was chosen in this study. The LDA classifier is simple, easy to implement, and computationally inexpensive. The classification rule for LDA is very intuitive. This method requires a training phase, meaning the computation of the discriminator function and their parameters. The new real-time data can be classified simply by solving the appropriate discriminant function for each class and applying the classification rule. The training dataset contains feature vectors and levels from the ground truth annotation. The feature vectors were computed in microcontroller environment, and then using those features, a classifier was trained in MATLAB. A 5-fold cross-validation technique was utilized to train the classifier. The parameters were determined from the training dataset and then applied to microcontroller environment for real-time application. For real-time implementation, the train LDA classifier was implemented in the embedded software. The embedded software was designed to execute the following operations in sequence. First, feature computation, and then find the responses using the trained LDA classifier. After the implementation of the classifier in embedded system, the R-level sensor system was tested on one volunteer. The volunteer performed similar walking and stair climbing sequence as mentioned in the data collection section. In this testing, completely different staircase and ground walking path were used. The accuracy of the model for different combinations of the features were investigated, and the results are presented in this table. The result shows that the addition of a new features did not increase the classification accuracy more than 1% after 3 features, which was determined to be the optimal feature number. Finally, the combination of this top 3 ranked feature was utilized to train the classifier and implement it in real time. The comparison of performance between training and real-time testing is shown here in the table. The accuracy, sensitivity, and specificity of the testing are comparable with the performance of the model on training dataset. The accuracy of the proposed model was 78.21%, while the sensitivity and the specificity were calculated as 90.48% and 86.75% respectively in real-time testing. The classification results of the proposed LDA classifier are demonstrated by the confusion matrix as well. In conclusion, we proposed a solution for real-time level ground walking versus stair-climbing locomotion mode detection by successfully implementing in a wearable embedded system. The proposed method is simple, easy to implement, yet effective enough to detect level ground walking versus stair-climbing. Three features were extracted from the sensor signal and the LDA classifier was used. The proposed model achieved an accuracy of 87.1%, sensitivity of 90.48%, and a specificity of 86.75% in real-time testing for around 26 minutes, which shows the initial proof of concept and demonstrate a great promise. Since the model was trained and tested with a small amount of data set, to further improve the performance, the model should be trained and tested with more data. In addition, the experiment was performed on 2 volunteers only, but with a higher number of participants, the model will be more person independent. In this study, 2 locomotion modes were considered only. However, in the future work, other locomotion modes such as stair descending, ramp up, ramp down, sit to stand can also be investigated. We'd like to thank National Science Foundation for their support, and thank you everyone for listening.